Hello and welcome to the Daily Space for today, Thursday, April 16th, 2020. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. Today's news is coming to us from all directions as astronomers, planetary scientists, astrobiologists all work to advance our explorations of the universe. As part of today's news, we will be joined by astronomer Riley Connor, who will be talking about his team's research into black holes bending light that we can detect through their reflections off of accretion disks. That will be coming up after the news, so plan to stick around today. Our first story is one that is near and dear to us. Yesterday, the OSIRIS-Rex spacecraft successfully completed a dress rehearsal of its sampling run down to the Nightingale crater. While they didn't actually reach out and touch Bennu this time, the mission did prove that the spacecraft can successfully deploy its sampling arm, retract it back into place, and both dive down and fly back up from where it hopes to eventually be, picking up some rocks to bring home. As part of the trial run, the mission team acquired amazing images of the asteroid's surface, proving once again that, Bennu is rocks all the way down. It's rocks on boulders with boulders and rocks with dust and more rocks. But these sets of images taken at a higher resolution than we have previously seen show that there is indeed this smaller debris that, the spacecraft is fully capable of picking up and bringing home. During this dress rehearsal, the OSIRIS-Rex mission traveled to within 75 meters or 246 feet of Bennu's surface. From this altitude, the team didn't just, check out that, yes, the landing site is actually as safe as we thought it was. They also acquired a bunch of scientific data, including spectroscopic data, that will allow them to understand the composition of Bennu in the region where this sample is getting picked up. Now, for the next several months, the team will be analyzing all the data, all the imaging, all the telemetry that they've received from the spacecraft, which is going to take a little bit of time to completely download. And all of this is going to be used for the mission to prepare for its, first attempt on August 25th to actually go down and collect rocks from Bennu. If everything goes as planned, OSIRIS-Rex will return that sample to Earth on September 24th, 2023. NASA and all the international collaborators have plans in place to keep the samples sterile that they bring back so that, none of our human bugs can get in and contaminate the science that we can do with this Bennu sample. Now, the other side of this is we're also going to make sure that nothing from Bennu can contaminate us. There are plenty of other places in our solar system that are more likely to host life than Bennu, but sometimes you act with all possible caution. Now, like I said, it's highly unlikely that the smashed up asteroid Bennu could be a host for any form of life. But one of our key questions is trying to understand exactly where in our solar system beyond our planet Earth that life could have formed. And this brings us to our second story of the day. This image is an image of our planet. No, this sadly has not yet been discovered on other worlds, but there is hope. To understand where to look for life, we need to understand how life came into existence. Over the years, folks have debated exactly where on Earth life could have started. And one of today's dominant ideas has life forming around hydrothermal vents, these places where under the ocean the surface cracks and heat and liquid and other materials escape, creating, the nutrients, the energy densities and the solvents that are all necessary for life, all in one place. Now, new work published in the journal Astrobiology shows how researchers in JPL's Icy Worlds team have worked to simulate the conditions of these hydrothermal vents early in Earth's history, bringing together, well, all of the chemistry, thermal conditions, and everything else that would have been there. This was part of the graduate work of Lauren White, who brought together the hydrogen-rich water such as flows out of these vents with seawater enriched with carbon dioxide and combined it with the same minerals that are present in these regions as we see today. Now, this was all done at the extraordinarily high pressures that are found deep in the Earth's oceans, as well as the moderate temperatures that seem most conducive to forming life and that also exist in some of these hydrothermal vents. And all of this was done at a scale sufficient for them to observe how fluids flowed and mixed. This was a large lab experiment, the likes of which has never previously been done. But when you're trying to, well, simulate the formation of chemistry required for life, sometimes it's go big or learn nothing. And they went big. This team has learned a lot. They found that the natural pulsations, pressures, and flows of hydrothermal vents are all capable of forming the organic minerals formate and methane. This is a significant step forward in this kind of research. And now Dr. White states, I think it's really significant that we showed that these reactions take place in the presence of these physical factors, like the pressure and the flow. We are still a long way from demonstrating that life could form in these environments. But if anyone ever wants to make that case, I think we'll need to have demonstrated the feasibility of every step of the process. We can't take anything for granted. If life can start at hydrothermal vents, this means our list of possible habitable worlds includes a myriad of icy moons right here in our own solar system, and more worlds than we dare count that are out there orbiting alien stars. This is truly captivating work, and I look forward to seeing how it continues to grow over the years to come. In our final story of the day, we are actually going to jump to something radically different, but still right here at home in our own Milky Way galaxy. We have one more confirmation that the universe is well described by Einstein's theories of relativity. For the past several decades, starting with Andrea Getz and moving on to teams of scientists all around the world, folks have been using massive telescopes and special techniques called drizzle photometry to directly measure the orbits of stars around our galaxy's central supermassive black hole. Now, a team using the European Southern Observatory's Very Large Telescope has revealed that one of the stars orbiting is not orbiting in the standard ellipse that we're used to when we think of, well, planets, asteroids, and anything else orbiting. Instead, its orbital pattern is more like that described by using a spirograph. This is a rosette pattern. And the reason that it has this orbit is, well, relativity adds to the precessional effects that happen in high gravity environments. Now to unpack this a little, every orbit precesses a small amount. This is a process that we see, but with Newton's gravity, we don't have to, we don't see this level of a switch. The normal precession is called episodal precession. But when we start looking in high gravity environments, what we see with the episodal precession and regular orbits as described by Newtonian physics is no longer enough. We start having to make relativistic corrections to this work. With 27 years of data and a 16-year orbit, it's possible to see with S2 not as many orbits as we have in the graphic currently up on screen, but there's enough data over its 330 measurements to see the, well, much larger precession that occurs in high gravity environments snuggled up close to supermassive black holes. This star, well, it's behaving exactly as Einstein would have expected. And this is just a nice result of a pretty orbit that, well, it took more than a generation of astronomers to produce these results. Billions of dollars of instrumentation, 330 measurements. And when it comes to understanding our universe, sometimes the things that seem easiest to understand, the orbits of stars, can be ridiculously hard to actually measure. But it's sure worth it when everything comes together in the end. Now, studying the effects of relativity is one of those things that is often easier said than done. More than 100 years after his publications, we're still working to observe in our universe everything Einstein predicted in his research. One of these predictions, that light can be bent by a black hole to actually orbit that black hole, well, that's research that was worked on by today's guest, who will be joining us in just a moment, Caltech postdoctoral scholar, Dr. Riley Connor. In just a moment, he will be joining us, and we're going to be talking about X-ray photons getting bent under the gravity of supermassive black holes and then getting scattered back to us thanks to reflections off of accretion disks. Now, I am going to put up the Be Right Back screen for just a minute while I bring on Riley. So don't go anywhere. The science will continue. Welcome back, everyone. As promised, I am now joined by Riley Connor, postdoctoral scholar at Caltech. Welcome, Riley. How are you doing today?
So you wanted a 30-second rundown of our work.
Yes.
So essentially, what I generally do is to look at data that comes from X-ray satellites that are observing black holes. Mostly, these black holes are a few times the mass or size of the sun. Sorry, mass of the sun, not size. And we look at them with X-ray satellites because they're very bright in the X-rays. The reason for this is that they accrete gas that gets very close to the black hole, and when it's in that region, it's hot enough so that it mostly shines in X-rays. What we did is something that a lot of people do when they look at these spectra, is they look for signatures of light that comes from that gas but gets reflected off this disk of material that is spiraling inwards. The difference between those kinds of studies and what we found is that usually the origin of that light is from some kind of what we call it a corona, which is obviously a slightly scary term to use at the moment, but it's basically a wispy gas, quite low density, very close to the black hole, just before the gas sort of falls in, that's even hotter than the disk, and it shines onto the disk, and we see the signatures of reflection in the spectrum. So normally that's what we're looking at. The difference between that and what we found in our paper is that the light itself is coming from this disk instead. So that's interesting to us because we know a lot of things about the geometry of that. We know a lot of things about how this disk looks and how close it gets to the black hole. So we have pre-existing information. And what we think we found is light that comes from that disk and actually gets bent right back onto itself. And that's due to the very strong gravity of the black hole, and the fact that it's spinning. We think it's spinning relatively fast.
And so I clearly have supermassive black holes in the brain today. Just yes, I was bad. This is a stellar mass black hole, so something that formed through the death of one or more massive stars. and this accretion disk is a nearby star getting cannibalized. Now, what exactly is the orientation of this system? I'm assuming you can't do this if the accretion disk is edge on to the Earth. Are we able to look straight down on this system in the plane of the sky?
Yeah, so of course, we know of, say, dozens of these systems in our own galaxy, right? And it's true that they could be inclined with respect to our line of sight at anything between 0 and 90 degrees, 0 being the disk faces directly at us, so we're looking down on the plane, and 90 meaning it's edge on. In this particular system, that actually is quite confusing. We know, for example, what the inclination of the binary is, meaning we know what the inclination of the orbit is with respect to our line of sight, and that's 75 degrees, which is quite edge on,
Yeah.
which does make, you would expect, make the emission that we see quite a lot fainter. However, when we look at this reflection spectrum, we call it, so when we look at this light bouncing off the disk and the signatures that are in the X-ray data, what we see is that the inclination is probably a bit lower when it comes to the actual disk of material. And that's also another interesting element of the work that we did. We think maybe that there's some warping of this accretion disk. The disk itself is getting warped by the fact that there's a very strong, there's a very massive black hole that's spinning and perhaps has effects on the shape of the accretion disk itself. That's another element of the work that we did. Yeah.
Now, when you go looking for these reflected photons, I come from a background in visible light where when we're dealing with photons, we're dealing with them by the thousands, tens of thousands, more of them than we would like as they saturate our detectors. But X-ray light, I don't think people appreciate how few photons you are dealing with. With a typical data set, a single pointing of your spacecraft at your source, how many photons might you be looking at?
Sure, it's a good question. So in this particular case, the instrument that we got our data from, it's no longer in operation. It ended in 2012. This is the Rossi X-ray Timing Explorer. So this was a NASA X-ray mission. It ran for something like 15 years. And this particular telescope was very good at collecting, with respect to X-ray astronomy, a lot
Yes.
of photons. So actually what this instrument would do is it would take snapshots. So it would look at these objects for something like an hour at a time. And in the space of that hour, you could collect somewhere on the order of 1 million X-ray photons.
Oh, that's sweet.
A lot. That's quite a
Yeah.
lot for an X-ray telescope. There are plenty of others that are more specialized in, say, spatially resolving objects. So, for example, there's the NASA mission Chandra. This is
Yes.
very good at spatially resolving objects and looking for faint things as well. But you're not getting, you're not always getting a huge number of photons. So this is all to do with basically the collecting area of the satellite, of the telescope. And in this case, we actually had quite a lot of photons, good sensitivity, which is exactly why we're able to look at the shape of this spectrum to quite a good statistical detail.
And with spectral work, what you were doing is looking at all the different energies of the photons coming back. And so you have photons that are being generated by the accretion disk and just flying straight at us. And then you have the photons that are getting bent around and reflected back at us. And what what are all the different things that couple together to change the color of those bent and reflected photons in this massive gravitational field?
Sure, that's also a very important and good question. So let's say, to try and keep this as simple as possible, we have some shape of emission that comes from this accretion disk that we see all the time in these spectra, right? And we can characterize it fairly well. We have a good model for it. So let's say we put that model in and we already know what that looks like. Well, when we actually look at the data, we see some different features in that spectrum. And the key things that we see, and I'm just going to talk about one of them, in fact, one of the key things we see is an emission line in the spectrum, so a sort of peak in the spectrum that comes from iron.
Okay.
So there's actually, this gas comes from a star, so there's a certain amount of different elements inside this gas. It's not just elements, even up to iron, a small amount. And you see an emission line from that iron that's very, very strong, and it appears in the X-ray energies, in the X-ray wavelengths. So we use that signature in the data. We model that with our model for what this reflected emission should look like. So that's how we differentiate. And now it's a little complicated to ascertain exactly how much is coming from this reflection and how much is coming from the disk. But that's why we take our data, get our models, and use our statistics to fit the models to the data. And
So
that's how we arrive at our result.
so let's unpack this a little bit. We have a super hot disk of material around this stellar mass black hole. In this spiraling mass of material, there is ionized iron that is giving off light in a very specific color that if it was just hanging out in your lab, you'd see all of the color in a single spike of light. Now, because it's in a whirling disk of gas, some of it's getting redshifted towards us. Sorry, red shifted away from us, blue shifted towards us, and that broadens out that line.
That
Now,
is correct.
in addition to broadening it out due to the Doppler shift, you also have the specific bending part. So it's the asymmetry in what we see, the fact that it's not just a line broadened by the rotation of the disk, but that line is asymmetric that allows you to say, oh, there's something else going on. Is that?
Yes, and what one of the key things. So you're correct about that, and that's generally true. If the emission, the gas that's emitting, if that can get really, really close to the strong gravity, and that happens to be dependent upon how fast the black hole is spinning. So if the black hole is spinning very fast, this material can get closer to the black hole and still spin around it before it falls in.
And
If
this is because the event horizon changes shape with the rotation rate of the black hole.
Exactly, yeah. So this gas can get closer and closer, and so that effect on this emission line that's in the X-ray spectrum, that effect becomes stronger and stronger the closer and closer this gas can get. Now, when it comes to the fact that we think we're seeing, how do we say, okay, where did that light come from? Did it
Right.
come from this disk, or did it come from this more wispy material that's floating around the black hole? And the way that we did that is that we looked at the shape of this reflected spectrum, and it looks like it comes from the emission from the disk, because we know the shape of that emission, we know what it looks like in the spectrum,
Mm-hmm.
and it looks like the reflected emission comes from something that was shining on the disk that looks like that disk spectrum, right? And that's how we differentiated from these two regions, and that's how we know that we're seeing the light coming from the disk and going back. And that's the part that's new about this paper, and nobody had seen that before.
Right.
We've had studies of this reflection spectrum, and we always thought that it mostly originated from this wispier gas. So this is where the difference is.
And so where it gets trickstery is in trying to differentiate which part of that ionized iron line is coming directly from the disk versus is bent light. So what are the things that affect the color of the bent light that leads to being able to differentiate it from the direct light?
So that's again a very good question.
I'm sorry. I really don't mean to be torturing you. I'm a I come from another area of astronomy, and rather than having to go through and do a literature search, I can
So,
just
so
ask you
that's
questions.
something. Sorry.
I was just saying, rather than having to do a literature search, I have you here and can ask all my difficult questions. I don't mean to be giving
True.
you an oral exam.
So the 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 way to differentiate that is we develop code models that can describe how all the different effects that are happening when this light is emitted very close to the black hole, and how it, what the paths of all the photons are, how their energy changes, and that is quite complex, and very strongly dependent on the geometry, the setup they have. So if this emission comes from this more wispy gas, then the way the photons will be affected will depend on that. If the emission comes from the disk instead and then is bent back, that will have a different behavior. The photons will shift in energy in particular ways. There are loads of effects that are occurring there due to the fact the disk is moving, it's spiraling. So you get, like you mentioned already, you get Doppler shifts just due to the fast motion of the gas. And then you also get these gravitational redshifts, we call them. So this is the strong gravity of the black hole reducing the energy of all the photons that are coming from gas very close to the black hole. So that will, again, that causes the shape of this ion line to broaden. But just so I'm very clear on, I think a way to answer fundamentally your question,
Yeah.
the emission coming from the disk itself. This is really dominated by what we call the continuum. So it's really what we call black body emission. So you can take the temperature of that inner part of the disk and very easily describe what the shape of the spectrum will be, and that's usually what we see. When we see the ion emission, we know that that's because material has to be heating up the top of the disk.
Right.
So it has to be from reflection. So that part is
Okay.
already fairly well ascertained.
Okay. So here you get to essentially shortcut the system where the accretion disk on its own is not producing the iron emission, but you get the iron emission strictly from reflected light.
Yes, and that's precisely because you're really over ionizing this top layer of gas. You're heating it quite significantly, and you benefit from having very, very high energy photons doing that, right? So they're striking the top of the disk. Very high energy photons cause a lot of that ion recombination and therefore emission from the ion line.
So the disk is essentially heating itself up through what might be described as a gravitational greenhouse effect, where the light can't escape due to gravity pulling it back the same way infrared light can't escape here on our planet because the atmosphere won't let it out.
That's a very beautiful way of describing it, actually. Yeah. Yeah.
So when you first found this, I mean, it's you're an astronomer. This means you periodically, like all of us, get the crank emails of I have discovered how to get rid of relativity. What was your like inner evil demon saying when you found yet one more way to prove relativity is true?
Um, yeah, I mean it's pretty exciting to make a contribution like that. I mean, I I, I suppose I would stress that I I don't think that our work is necessarily a proof, because it's not one of these very strict and fundamental tests, but it is, it's a contribution, and
Yeah.
yeah, it's a good feeling actually to do something where you find something slightly new, and it also confirms that, okay, things are working the way they should be.
It's the ability to look at this email, which you should never respond to. All of you out there, do not feed the trolls. Um, it's this chance to say, look, my research wouldn't work without Einstein. And that can be satisfying even if you never say it to them, but you can think it to yourself.
Absolutely.
Now, with all of the effects going on, um, you've found this in one system so far. As you said, there are a myriad of different systems out there that you've been looking at. What was it that made it possible to find it for the first time in this system? What makes it special?
Oh, it's, well, like a lot of things in scientific research, just total chance. We This data was already, like I said, it comes from an instrument that's already decommissioned.
Yeah.
So the data was there, and actually the observation was made in 1998. So the data's been there for a long time.
Yeah.
The difference is we just tried a different model. Um, we just said, okay, this doesn't seem to be working the way we're already doing it. Let's try a different model, and it really worked very well. And that's what gave us this impression that, okay, we may have found something that's more realistic here. We started to look at data from different instruments, different sources, as much as we can find, and doing the same thing. And we're trying to develop the models as well, because what the model we tried is a very limited version of what we think the truth is. So we're developing the models, looking at more data, and we think we're finding it in other places. So we hope there'll be a lot more work on this in the future.
And the importance of models in observational astronomy is something that often doesn't get acknowledged. When I tell you that my spectra say there's this particular set of elements in a star, what I'm actually telling you is when I take that spectra with a telescope, I then sit down at a computer and I type into the computer, okay, so now fit in this atom, now fit in this atom. And I adjust the ratios of this atom to that. I adjust the surface gravity of the star. I adjust the rotation rate. I adjust its velocity through space, all in my software, until what my software outputs exactly matches what my telescope saw. And I've only done this with like regular everyday stars, which are much more simplistic in terms of the number of variables you're contending with. Um, with what you're doing, you can't yet put in all the actual variables of what describes that system to try and get at it. So you're adding in one variable at a time and tweaking it until it matches your data. Now, one of the things that was mentioned by you earlier was the effects of how the black hole rotates. And uh, most of the time people are like, we're just going to like treat this like there's no black hole rotation because we don't quite know what to do with this. What is your future ability to be able to actually see black hole rotation with this kind of a data set and matched modeling?
Again, very good question. So this is something that we do all the time already. As I said, assuming that this emission comes from this wispier region of gas. Now, the geometry of that wispy region is uncertain. It's very
Right.
uncertain. We don't know an awful lot about it even
And
now.
what's the source of the wispy stuff?
Oh, okay. So that again is slightly difficult to answer. It's
There can be multiple answers and you don't know which one is right. That's fine.
the source is still from this spiraling accretion disk, but it's just gas that manages to get hotter. So because it gets hotter, it expands, and that's the simplest way of looking at it. So this wispy region is just hotter gas that's like thicker in geometry, and beyond that, we don't know much more about what it looks like.
Okay.
We just know it's hotter and it behaves in a certain way, and it produces a certain type of emission. Um, the difference between looking at the reflection of emission coming from that region and seeing reflection that comes from the emission from the disk itself is that we know very well how that disk behaves. So
Yes.
now we have a slightly different way of measuring, a slightly better way actually, of measuring the spin of the black hole. This disk, we know it gets as close as it can to the black hole. In particular times, it gets as close as it can. And as close as it can be depends on the spin. Very
And
explicit.
and to unpack this a little, that accretion disk goes all the way through the event horizon and down to whatever physics is dictating inside the event horizon. But we only can see it to the edge of the event horizon. It's not like it gets to the event horizon and says, "I'm done here. I shall stop now."
Yeah, so the way that works, so if you want to calculate, a little piece of material, what happens as it spirals towards the black hole, what you find is a location that we refer to as the innermost stable circular orbit. That's a
Right.
lot to unpack, but that's basically how close can you be and still be rotating like this around the black hole.
Okay.
Uh, beyond that point, and that's slightly larger actually than the event horizon. But beyond that point, then this gas would start falling in a slightly different way, and then it goes into the event horizon, and then we don't know what's happening with it, right? I mean, you can come up with a mathematical model, but we're not going to see light coming from it.
Right.
But this innermost stable circular orbit really depends, in a very clear way, if you use Einstein's theory, on how fast the black hole is spinning. If the black hole spins faster, you can get closer. This innermost stable circular orbit is closer. So that's how we know that the way this emission will appear is going to depend very explicitly on the spin, and that's part of our models. And this is therefore a powerful way of measuring spins.
And so at this stage in your research, it sounds like you're able to say a non-spinning black hole model doesn't work, but you're not yet at the state of saying this black hole is rotating at this speed plus or minus X. Is that fairly accurate?
Somewhat. So it's complex. The problem you have there is that if the black hole is not spinning very fast, it by definition it becomes slightly more difficult to determine how fast it's spinning.
Right.
Right, and this is just because it's a non-linear effect. So once the black hole is spinning at half its maximum, it's very similar to if it were spinning at 10% of the maximum, and it's very hard to differentiate. But if the black hole is spinning like as fast as it can, then actually if we measure that, then we can say, okay, it's definitely spinning at least this fast, like it's spinning quite almost maximal.
So what is the limit on a black hole's rotation? What forces of nature say, and thou shalt not spin faster?
It's really set just by the. I mean, if you wanted to look at it in real units, so if I wanted to say it spins this many times a second or something like that,
Right.
would be set by the mass of the black hole itself. That would be like the real physical limit, because the mass of the black hole tells me how big it is as well.
Okay.
It's 1-to-1 basically. So if the black hole is only mass of the sun, the size is something like a few kilometers. If it's a supermassive black hole, then it's a million times that. So that how fast it spins in real terms would depend on that. The way we look at it is what we call a dimensionless spin. So this is something between 0 and 1 being as fast as it possibly can. And this is just a stability argument. You can't spin any faster than that before you break the speed of light limit.
Okay. Okay. That makes sense. Um, yeah, even black holes can't break the speed of light. This is the way our universe works. And just as a note to all of you out there in our audience, when you're doing a lot of relativistic calculations, you start doing things like C is now 1. And it's just a different way in which you break things down into dimensionless units to start dealing with what is the physics instead of having to deal with what are the numbers we have measured experimentally. And then you plug the numbers in and put it back into the universe we're used to measuring with rulers and Doppler shift, and carry on with your calculations. So as you move forward, what are the things that you're most hungry to try and find in this data?
Yeah, so as I said before, we're developing our models, and for example, I've had time accepted with an X-ray satellite that's also very good at collecting a lot of photons, because that's what we want.
Right.
So I want to hopefully catch another one of these black holes that starts getting really bright in our galaxy, and try and get as good an X-ray spectrum as I can to use our models and get even better constraints on this emission that we think we're seeing, and hopefully catch this object in a particular stage so that we can really measure the spin very well with this technique. That's what I want to do in terms of this part of my work.
I'm particularly fascinated with all of this because when I was in graduate school back in 98, uh, we still talked about how there were no definite black holes confirmed. There was Cygnus X1 that we kind of assumed was a black hole, but it wasn't certain. And we've gone over the course of my professional career from we're pretty sure there's black holes to a couple of years later, my dissertation advisor, John Cormody, was one of the people who figured out yes, supermassive black holes are black holes. We don't need to keep drawing monsters in our overhead diagrams. Because I kid you not, that is what faculty did when I was an undergrad. They drew monsters in the centers of black holes to try and explain what we don't understand. And to see all of the specificity that has been added into our understanding with these telescopes, it's really kind of amazing. And right now in astronomy, we're working as a field on the decadal survey to try and define what are the things we need to focus on in the next 10 years. And if you could have the attention of the entire decadal survey committee and say, this is what we need to do, what instruments, what spacecraft would you dream of to keep doing this work?
Oh gosh, it's a big question. So there are a few different things that I think would be beneficial in my area of work, and some of the things are already being done. But for me, we want different missions that complement each other.
Yes.
And that is, true for X-ray astronomers, but also across the entire spectrum. Because, for example, these black holes that I study, you can learn things about them across the entire spectrum: gamma ray, X-ray, optical, UV, infrared, radio. They shine different parts of this accretion flow shine in different wavelengths. Um, so for me, you want as many capable instruments that can work together across the entire spectrum, but specifically in the X-ray, you want something that's very capable in the it's like lower energy X-ray band, but you also want something that's very capable up to very high energies and able to work together to observe, to get yourself a spectrum that covers this entire range. There's also another more specific element, which is X-ray polarization, which is something that there are a couple of missions already approved that are going to be developed into the future, into the next decade or so, to try and launch and look for polarization signatures. So this is just the orientation of the light as it's traveling towards us, essentially. Um,
And polarization is affected by or caused by reflections, magnetic field interactions. It's diagnostic of what the light has experienced on its way towards us.
Exactly, yeah. So it can start helping us to establish what kind of emission process we're seeing and what sort of geometry we might have that could cause the light to look like this in terms of its polarization. Exactly the way you just described, yeah. So this is something that I'm excited about for the future as well.
Now, if you could get your hands on the Event Horizon Telescope Consortium, what might they be able to see with these systems that you're looking at these amazingly high radio resolutions, which is admittedly completely different color than what you're looking at, opposite end of the spectrum, but is nonetheless how we're able to start resolving accretion disks?
Yeah, so I mean, if the Event Horizon Telescope, and actually I was sort of mildly involved in the early stages. I used to go to some of their meetings when I did my PhD. The they, if they were able to do what they did at the correct wavelengths to see this in these smaller black holes that I'm currently studying,
Yeah.
they would see something quite similar. But the power of what the of for example, this wispy gas I keep talking about and what it looks like and how it behaves, how it emits light, they would be able to answer a lot of those questions that we still have right now very, very well.
Could could
Because
they could they answer about the warping of the disk, for instance, that you mentioned?
ooh, that's again a good question. I would expect so, yes, because if they could see this disk as it's down at the innermost stable circular orbit that I was talking about before, if they could do that, what they would see would depend on how inclined it is.
Yeah.
And they would be able to say, okay, it's definitely, inclined like this, and the orbit is not. So that would tell us, well, there has to be some warping. So yeah, this would really help to answer those kinds of questions.
That that would be super cool. Now, I suspect you're limited in only being able to see these systems within our galaxy. What How far out can you go in looking at these things?
That's again an interesting question, because there are actually some other objects that. So I work in a team at Caltech that runs an X-ray satellite. It's called NuSTAR,
Uh-huh.
and a lot of the science that they do is looking at what we call ultraluminous X-ray sources. So these a lot of work on these, so I don't want to talk about certainties of what we, in terms of what are they really. They may be
Yeah.
neutron stars or black holes. We're not entirely sure. The emphasis is now that they're probably neutron stars. But these are accreting compact objects, just like what I study, and they're in other galaxies. They just so happen to get that little bit brighter. They get bright enough so that even though they're in another galaxy, we can see them. So this is really the limit. The objects that I study in our galaxy, if I put one of those in another galaxy, I wouldn't see it. But
Okay.
if you make it, an order of magnitude or so, maybe two orders of magnitude brighter, then you would be able to see it. And that's why we see these ultra luminous X-ray sources.
Now, this question is me simply being curious. Um, you would have nominally, I think, the potential to differentiate between the smallest black holes and the largest neutron stars in binary accreting systems by looking for this kind of reflection. Is that correct?
Yes, I mean, absolutely. The reflection will look different. The nature of the compact object there is fundamentally different. So you would expect to see some different behavior in terms of how close this accretion disk can get, and that's already the case. We already can differentiate, broadly speaking, by looking at how the X-ray spectrum looks, and we can say, okay, that looks like all these other systems that we know are neutron stars, and whereas this one looks a lot like all these black holes. The other way to do that, to tell the difference, is to try and measure the mass of that object.
Right.
And that's typically done by looking at the orbits. So the star, as it's orbiting around the compact object, you do your calculations of the gravity, and you can say, okay, I know the mass of the compact object is 1 point something times the mass of the sun. It's definitely a neutron star. It's not a black hole. If it's more than 3 times the mass of the sun, well, that can't be a neutron star, because we know that they become very unstable at those masses, and they would become black holes. So that's typically how you would get a very definitive differentiation. But signatures in the X-ray spectra also tell us things about whether they're black holes or neutron stars. That's true.
And there's always that person in the back of the room with the but if it's rotating, it could still be a comment, and this might be a way to say no. We have looked. It is not an overly fast rotating. It is a and it's always good to be able to directly knock out this is this and this is that, where the boundaries start to get fuzzy as you add in extra characteristics beyond just the mass of an object.
Absolutely, yeah, that's definitely true.
This is really cool work. And again, I am sorry if it feels like I'm putting you through oral exams. I really had a lot of interest in what you're doing. And what what are you hoping to do next with all of this?
Sure. So, I mean, I have a few different projects on the go, but this one is definitely a priority. And I have some of the co-authors that are on the paper that I wrote. Um, One or two of them specialize in doing these calculations and developing these models for how would this reflected spectrum look like. So they're now currently, going back to the drawing board and trying to figure that out and develop their models further. What we hope is to come up with a more improved model, and then say, okay, now let's take that and apply it to as much data as we can, and that will be something that I'll hopefully do. So that's where I want to go moving forward. See if we can actually use this to make better estimates of the spins and things like this. See if we can start breaking degeneracies that we have in this field.
And this sounds like it's a wonderfully cyclic process where you go through, you find the data, you process the data, you apply the model, you update the model, you reapply it. And yes, you want new data. Everyone wants new data. But you can do so much simply by taking advantage of improving computational abilities on, well, our overpowered graphics cards, basically.
Yes, yes. You want to make the most out of all the data that we already have, which is actually really what I've been hired to do. Is we have new models, let's apply that to the older data and see what we find. We might as well because it's there for free.
Exactly. And I have to admit, having experienced more clouds than any normal astronomer has ever experienced at McDonald Observatory, I only use survey data now. I only use archival data because you don't have to worry about your spacecraft blowing up or clouds getting in the way when you use the already existing data. So you're definitely doing things the smart way in so many different ways. So if people want to follow up on your research, where should they look to keep learning more about what you're doing?
Sure. So there are a couple of places you can go. They're all branches of the Caltech website, essentially.
Yeah.
So, for example, if you want to look at the type of science that's coming out of the team I work in, the
Mm-hmm.
group I work in, you can go to newstar.caltech.edu. Newstar is NUSTAR, NUSTAR, and Caltech, CALTECH.edu. So this page will show you all the science that's coming out of the group I work in. And like I said before, we're a group that runs this X-ray satellite called NewStar, which is a NASA mission. You can also go to the personal work page of my boss, actually. He has some of the details of the different work that we specifically do on these accreting black hole binaries. So that's srl.caltech.edu /personnel/Javier. That's JAVIER.
That
If you go to that page, you'll see the smaller group that I work in within this larger group, basically. And you'll see the type of work that we do, and anything we start to do in the future. There'll of course be links to papers that we write and things like that.
that that is all awesome. Now, is there anything that I didn't ask you about that you were really hoping for the opportunity to say during this interview?
Nothing springs to mind. I think we covered quite a lot.
Well, this has truly been a pleasure for me. I'm thrilled to get to pepper you with all these questions, and thank you so much for joining us today, Riley. This has been great, and I wish you the best in all your future endeavors and just getting through these super strange times we're in when it's really hard to be a junior researcher. We're here anytime you want to get your research out to the world.
Thank you very much for your time.
Okay, and I'm gonna switch over to having the chat on screen. Thank you, Riley. And thank you, everyone, for being here today. This has been a special extended episode of The Daily Space. And Zoom has its issues, but it's allowing us to stay in contact with one another. And we're going to do everything we can to, well, when we see a scientist doing really cool work, we're going to bring them on, and I will apparently accidentally put them under oral exams in the name of science. So that pretty much rounds out what I've got planned for today. As always, my name is Dr. Pamela Gay, and I wrote today's episode and then inadvertently tortured Dr. Riley Connor about his research. This episode will be produced by Susie Murph and is a production of the Planetary Science Institute. We are a 501c3 nonprofit dedicated to exploring this solar system and beyond. We are here thanks to the generous contributions of people like you. We are here thanks to your bits, thanks to your subs, thanks to your patronage over at patreon.com. And thanks to you being here as a support in the chat, asking us questions that encourages us to go on, and all your volunteer efforts helping us, well, keep everything going behind the scenes. We wouldn't exist without you. So thank you for being here. And we just want to remind you, if you're having a tough time with COVID and the quarantine and the isolation and everything that's going on, we get it and we're here for you. Join us over on our Discord and just say, hi, can I have a human to talk to? We've got humans and we're bored too, or we're not always bored, but we're desperate to talk to humans too. We're here. And just a reminder, if there's someone else in your life that you think might be interested in this, share science, share us with them. You never know whose life you're going to change by giving them a daily dose of space. Okay, I see those bits coming in, Broken Symmetry. I see those bits. Thank you. Thank you so much. This is how we pay Annie and Susie for everything they do to keep us going. Thank you. All right. So I need to go work on making the science flow. Thank you, Wayne Johnson. Thank you. Thank you all so much. All right. So I'm off to try and make the science flow. Who shall we raid, dear humans? I see Prof. Milko is streaming. Is there anyone else out there you'd like to see? I'm just going to ask you. I don't know where my Discord window went at the moment. I'm sorry that I don't have time to answer questions today. I need to figure out how to make this work better on days that we have guests. We will have a guest again tomorrow. We are having one of the researchers who studies Betelgeuse come on to help us understand what we do and don't know about that red giant's recent fading and rebrightening event. Oh, Horizon Psi is on. Okay, we haven't rated Horizon Psi in ages. So let's raid Horizon Psi. Okay, so here we go with the raid. Is anyone covering AWS Astronomy Live broadcast? I don't know what that is. Let me know about it over in Discord, Broken Symmetry. We'll cover it if I know what it is, and we can. Anyways, wherever you are in the world, thank you for being here. Thank you for making us part of your breakfast, your lunch, your dinner, whatever meal it is that you have been eating. And I hope to get to know more of you over on Discord. Anyways, that's all I've got. So wherever you are in the world, have a fabulous morning, evening, or afternoon, and wash your hands. Got it? Got it? You're going to wash them, right? Right? Okay. I'll see you on the other side.